Uh, so hi everyone. This is a lecture on prefix sums and sparse table. They both are methods to solve static range queries, sum and minimum queries respectively. So first we'll start with prefix sum. It's a very simple idea, and it used in a lot of problems. Like it used as a small part in like part of bigger problems. So the main motivation problem is something like this. You have an array of integers, and of array of integers of length n, and n can be up to, let's say, 10 to the power 5. So n is quite huge. You can't afford a quadratic time complexity. And then you also have q queries, like q also can be up to 10 to the power 5. And each query is of the form l comma r, and you have to output the sum of elements in the subarray of l to r. So the naive approach is, of course, to just go through all the elements in each queries. And since this can be like this is very costly, because you can see that it can go up to O of nq, given that the queries are all huge. So and when n is 10 to the power 5 and q is also 10 to the power 5, this can go up to 10 to the power 10 operation, which will definitely give you a TLE. So to solve this more efficiently, we have prefix sums. So prefix sums, essentially what it just says, we store the sum of the prefix of elements up to I. So let's say we have an array like, then the prefix array of this would look like something 24. So P of I is defined as sum of everything from A1, A2, A3 up to AI. So you can notice that P of 1 is 1, and then P of 2 is A2 plus P1. So we got a general formula from this. So P of I is AI plus PI minus 1. And now this is essentially, this is very useful, because now we can use this to solve the queries much faster. Instead of having to go through the entire subarray from L to R, we can now do it in O of 1, which is much better, and this will definitely pass, right? So let's see how we can use the prefix sum array to compute those queries. So let me write an array here. And if I take some subarray in between this, let's say A3 to maybe something like this, we know the prefix sum, right? And this sum is nothing but, by the way, this subarray is from A3 to AN minus 1. I want to calculate the sum of elements in this subarray. This is one such query that I'm asking. And since we know the prefix sum is already calculated using this recurrence, you can calculate the entire prefix sum array in O of n with this, because this recurrence is quite simple. Now let's say we only want the sum of this. And how do we calculate this efficiently with the prefix sum array that we have computed? It's simple. It is just P of n minus 1 minus P of 2. So this entire thing would be counted in P of n minus 1, and then you're subtracting this P of 2 parts. So you'll be left with just this part. So that's how prefix sum works. It's quite simple. So now there's also a 2D variant of this, which is quite interesting. So basically you have prefix sums on a 2D grid, and you can answer queries to, find the sum of elements of subrectangles in those grid. This was also a direct problem in ZCO 2022 P1. It was just 2D prefix sum. If you knew 2D prefix sum, you would just get 100 on that problem. So the idea is similar, but it's slightly different. So I'll explain. Let's say you have a n into m grid. And there are elements in all these things. Each cell contains some element, like some integer, and we want to find, let's say, the sum of elements in this subrectangle. And the constraints are also similar. N into m can be 10 to the power less than 10 to the power 5, and that you have again q is 10 to the power q is less than equal to 10 to the power 5, and you want to answer queries of the form find the sum of elements from the sub, like you're given the top left corner of the rectangle that you want to compute, so that is L1 R1 and L2 R2. So in this case this cell would be L1 R1, like you can also take x1 y1, it's the same thing, and this would be L2 R2. So you want to find the sum of all the elements in this subrectangle. And we can also do the same procedure, except the way you would actually do the queries is slightly different. So here also it's in this 2D prefix sum, what we would do is, so we would again make an identical array. This is the array of elements, and now we will make our prefix grid. So now what we would do is, suppose we want to find the value that would go in this cell for the prefix grid. This would be nothing but the sum of everything in the rectangle of L1 R1, basically from this grid. So this would contain everything over here like this. And let's take another cell for example. Maybe this cell. This would contain everything in this subarray. So now let's see how we can use this to answer queries for a subrectangle. Let's say we want to find the sum of elements in this subrectangle only. How do we do this efficiently in O of 1? Using the information we have only calculated, basically big subrectangle blocks starting from the top left corner. Using only that, how do we calculate the sum of this? So first, the obvious thing is to, of course, take the prefix of this. That would include this whole rectangle right here. Clearly, we have some extra part that we need to trim off. So then we would make a different color. Then we would subtract this part. And again, you can see that this part is again extra. So then we would also subtract that part again by taking the value at this cell, the green color dot here. And by the way, the yellow color is this dot, whatever the prefix value would be there at that cell. And but now you can notice that we have actually subtracted this red color portion here twice, right? So then we would just add it once. So to summarize, to calculate the sum of this blue color subarray, we would first add this blue part, this blue cell, and then subtract the yellow cell, subtract the green cell, and then add the red cell. So then effectively you will just be, shouldn't the green dots be moved 2 places to the left? Oh yeah, sorry. I thought it was the entire subarray. Yes, now it's right. Is it clear? I just made a mistake. So that's then effectively would just be left with all the elements in this blue subarray. Okay, I'll explain it again. So can you give me a rectangle that you want me to find the sum for, like any sub-rectangle of this? Just specify the top left corner and the bottom right corner. Okay, 3 comma 3 is the top left corner. We're starting from here. 3 comma 3 to 5 comma 7. So you want to now calculate. So you understood what we are storing in the prefix array, right? Basically, for each cell, we are storing this entire thing, subarray, like whatever is from the starting, from the 1 1 to that cell, whatever the sum is. That's quite easy to store. I'll actually explain how we calculate that. But right now, I just want you to know that we have calculated it. I'm like explaining how we answer queries. So now to answer your question, this subarray, let's say we want to calculate the sum for this subarray. So what we have calculated is, so this, the value of the prefix at this cell would include this whole thing. It's kind of a principle of inclusion and exclusion thing. So this prefix, if at this cell, the prefix value that is stored at this cell would include this entire blue color subarray. But clearly we only want the yellow color shaded part, so we have to subtract some extra stuff. So now what we would subtract is this green stuff, like this whole thing, because it's like it's not needed. And then the thing that would correspond to this cell would be that thing, because that's the sum that you would store in the green cell, right? Because the value for each cell is the sum of the subrectangle from 1 1 to that cell. This is 1 1 till that cell. And even at the top, we have a extra part. Let me do that in blue. Corresponding to this cell, we would now subtract this entire thing. And you can notice that this top left thing, the one has overlap in blue and green. It is being subtracted twice, right? So we don't want to subtract it twice. We just want to subtract it once because we only want the yellow color. So now what we would do is we would add this part. Does that make sense? So in the end, we are effectively just left with the yellow part. Okay. And now coming to how we would actually calculate everything in this way, because the prefix sum was kind of trivial. I gave you a recurrence. P of I is P of I minus 1 plus AI. But in this, I mean, this is also quite trivial, but I'll just explain it. So what you can do is, let us say you have a grid like this. And you want to calculate the prefix sum for this cell. So basically you want to calculate all the elements, sum of all the elements in this subgrid, because from 1 1 to that cell. So we will be going from top left to bottom right to calculate all the values. So when we have reached this cell in the for loop, we would have already calculated the cells before it to the top left of it, or even to the top of it, like anything that's not to the bottom right we would have calculated. So we know the value of this green cell and we know the value of this yellow cell. So now then what we can do is, we can again, this blue cell is nothing but this yellow cell, which we would have already calculated before coming to this cell, of course. And we will also add the green cell. But then again, you see there's an overlap, right? Because the yellow and green has some overlap. That would correspond. So we have to just subtract this red cell value because you're adding it twice. But we only want that whole thing to come once. So we are subtracting the red ones. Does it make sense? That's how you would calculate. Or you could just use the prefix sum for each row separately and just take from the top. I mean, it's your wish, implementation wise. But this is one implementation that you can use. So we'll go to some simple introductory problems of prefix sums. This is a CSS problem, quite basic. just try the problem for 2 minutes. Just give it like if it's the first time that you're seeing the problem. And if you have any ideas, you can put it in chat. Someone send their idea in chat. Why would you use a bool map? Because you want to count. You don't want to just check if there exists a subsequence with some x. You want to count the number of subsequences. I think the remaining part is correct, but it won't be a bool map. Okay, you're saying if map current sum is exists, but then there might be more than one instance of it, right? Because values can be negative. So the answer won't just be incremented by once. Like it can be more than once also if there were more occurrences of it. Are you understanding what I'm saying? Like if I understood the solution correctly, I think it's wrong. Like if you don't understand, you can tell. Like, I can give you. I can probably try to give you a counter example. Yeah, someone else has given. That is correct. It won't be a bool. Like yeah, everything is okay. Only it doesn't have to be a bool map. Yes. Why are you saying if it is zero, then res plus plus? Okay, I'll come to the solution now. It's so again, of course, we're going to use prefix sums in this. You can see that here we want to count the number of subarrays having some x. So we'll see how to use prefix sums. Let this be the array. And we will store the prefix array, of course. That will be p1, p2, p3, pn, where as I said, pi is the sum of the elements of the prefix of length I from 1. So let's see what is the criteria required for a subarray to have sum x. When is it true? So as I said, if you want to count the sum of elements from L to R, the subarray L to R, this would be given by prefix of R minus prefix of L minus 1, as we saw in the motivation example. And we want to find all the pairs, like number of pairs L. The problem is basically the number of pairs L comma R such that PR minus PL minus 1, the sum of elements from L to R, that is equal to X. So, and we are looking to solve this. Of course, the naive algorithm would be to do it in O of n squared, go through every possible L comma R and check if it satisfies. But that will TLE because n is less than equal to 2 into 10 to the power 5. So we are trying to solve it in something like O of n or maybe O of n log n. Maybe that log will come from a map. So let us. So now we'll see what to store and how to solve this. So this now we can rearrange this to something like this. So now what we will do is we will solve this O of n. So we will iterate through 1 to n. And when we are at each position, we will try to count the number of pairs. Let's say we are at position I currently now. We will now try to count the number of pairs L comma I such that L comma I satisfy the condition in the question. The sum of elements from L to I is X. So does this make sense? We're going through each I from 1 to n. And during that each I, we are calculating the number of pairs L. Of course, L is less than or equal to I such that this condition is satisfied. And when we are at a position I, of course, P of I is fixed. So that would be P of R, analogous here. P of I is, so P of I is fixed for a given I. We are calculating the answer for a given I right now. And X is also fixed. So now we see that the value of P of L minus 1 is also fixed, right? And since L minus 1 would occur before I, we can store the number of occurrences of this value that we require. Does it make sense in a map? Like P of I minus P of L minus 1 has to be X. So when you're going from I, after we have calculated for that particular case, what we would do is we would store it in a map. We will store the value of Pi in a map so that we can use it for further use, because we can see that the value of P is coming later in use. When we want to calculate the pairs L comma I, such that L is before I and I is the current index that we are calculating the answer for. If you have any questions still here, you can ask. So to formalize it, for each I, the answer would be incremented by the answer would be incremented by basically how many, like the number of occurrences of Pi minus X, because that is the P of L minus 1 that we're looking for, right? So the answer would be incremented. The answer would be incremented by the count of Pi minus X. And then after this position, after we have done this in that iteration, we would also update the count of P of I would be incremented, because then we would now use this prefix for a later index to calculate the answer if we need it. So does this make sense? This is basic solution. And you would also add a base case, like since we can also not have any element, right? Like we can take the subarray from the starting index 1 to I. So then we would also you would have count 0 as 1. Like before doing anything, before any for loop, we would just set count 0 as 1. If you have any questions still here, you can ask. By the way, this count is a C++ HAD map. So we can see that we are going through n iterations. And for each iteration, we're accessing a map which can have size. Actually, the size can be huge, like because there are many elements. So we'll just assume log. So the time complexity is n log n because we're getting the log from accessing this and storing items in this map, and we're having n iterations. So the time complexity would be n log n, which would comfortably pass this problem. Okay, so now I'll move on to the next problem. Do give this problem a try. It is also quite similar to this problem. Uh, you can take 2 or 3 minutes, and if you have any ideas, do put them in the chat. I'll try to answer if they're like to tell if they're correct or not. Take x now size of subarray, but do you understand that the size of subarray won't be constant, right? Because for different L comma R, like in the previous problem, the sum was constant, no matter it didn't depend on L comma R, but the size would now depend on L comma R. Does that make sense? So again, the strategy is just to try to formalize the statement, like write the condition down mathematically. You'll notice what to store in the prefix summary, like how I did for the previous problem. P of I minus P of L minus 1 is x. So from that I got some relation. So you can do the same thing in this. Okay, I'll present the solution now. So the strategy is the same. We just try to formalize the condition given. The condition given in the problem is so we want the sum of the elements to be equal to the length. This is almost similar, but then the length is variable now. It's not a constant, so it's not that simple either. So now again we try to formalize this in terms of our prefix sum array because that's what we're learning right now. We'll try to write it in the form of prefix sums. The sum from L to R can be written as P of R minus P of L minus 1. And we want this to be equal to R minus L plus 1. This is P of L minus 1. So I just wrote this minus L plus 1 as minus of L minus 1 whole bracket thing. Now the advantage of doing this is that we can now transpose the variables. P of R minus R, I took R to the left hand side, and P of L minus 1 minus L minus 1. So I hope you see the advantage in doing this, because now we have something symmetric, or you can say homogeneous for R and L, right? Like they're kind of the same form now. So now rather than doing something on the sequence P like we did in the previous problem, we will now do something. Let's define a new sequence, let's say capital A, which is P of I minus I. Now the problem just boils down to, so you can notice that P of R minus R, P of L minus 1 minus L minus 1. So now the problem just boils down to finding the pairs L comma R such that AR is equal to A of L minus 1, or you can just say AR is equal to AL in a sense, because you just want to count the number of pairs of indices such that the sequence A has the same value. Does this make sense? I just transposed some variables and I defined a new sequence. That is P of I minus I. Rather than just Pi, it is P of I minus I. And this now it's a very simple problem. We can of course compute the whole sequence. Let's say we have some A1, A2, A3 up to AN. Now we have to just now we have to compute the sequence P first, or we can just compute A directly. A is nothing but the prefix, the sum of the prefix of length I. AI is Pi minus I. And again, this problem now it is just the problem boils down to finding pairs L comma R such that AL is equal to AR, and A is defined here Pi minus I. So now what we'll do is, again we can store a map, because I think A can be huge. It's up to a billion. Oh no, actually A is small in this problem, but like you can use a like array also, or you can use a map. Like I'm solving a more general problem here. It's just digits and it cannot go up more than 10 to the power 6. But I'll just use a map here. I'll use a map, and I will go through all the elements of A, and I will store the count of each element that is occurring in A. Let us say some element x, the value of A, x is the value of A. If, let's say it is occurring y times, then the answer would get incremented by y into y minus 1 by 2. Basically, y choose 2. It would be incremented by y choose 2. If some element, for every element that is in A, let's say it's occurring y times, we can store this in a map by just iterating through the array A from 1 to n. We can store its occurrences, and let's say it occurs y times in the whole array A. We want to calculate the number of pairs such that the value is equal. So a value is occurring y times. So how many pairs can we, get out of it such that the value is same? That is nothing but y choose 2, right? So when y choose 2 is y into y minus 1 by 2. Does this make sense? If anyone has a different idea, you can share. Like if you thought of doing something else. Okay. So now moving to a. Oh, sorry. Yeah, I did undo. Can you see the screen now? I don't understand what you want. Just opening it down. Okay. So now I'll share a problem. The last problem on prefix sums. Like prefix sums are like used in almost every problem. Like it's a very small part of the small part of the problem. Like it's used in DP optimizations and whatnot. It's very hard to find good problems that use just prefix sums. So our last cat coder problem. Do give it a try. It's really interesting. It's slightly different from whatever we have done till now, but still it's easy nevertheless. You can take 2 to 3 minutes on this one, and if you have any ideas, do put them in the chat. Oh, sorry, what muted. I'll not spoil this problem. I can give you some hints, and you can try to solve it by yourself. It's slightly challenge, like a more challenging problem. So I will give you some hints after some time, like maybe 2 minutes. It's fine if you're not able to solve it, like, especially for people who are learning prefix sum for the first time. It's not very obvious. You mean by substring, you're just taking the value in uh, like base 10, basically the whole number as it is. Okay. I don't want to spoil the problem for others. Yeah, but that is correct. Basically, instead of prefix array, it is suffix array. That's a big hint. You people can try it with that now. You can do something with suffix. And do give this problem a decent try. It's not easy. That's just hint. You can use suffix and something to do with decimal representation. Clearly, because you need to do something with divisibility, right? 2019 or something being divisible by 2019. I'll also attach one more at coded problem, which is slightly simpler than this. You can also try it after the lecture. You can try it, and then if you have any doubt, you can discuss it in the SPOI group. It is PIth or something. I think PIth minus PJth. I think that's what you mean. And the prefix is not exactly the sum of element. It is, in as I said, something to do with decimal representation. You have to multiply with powers of 10 and stuff. Yeah, you said something like that. So you can try it after the lecture. And even the other problem that I said, you can try it. So now I will move on to sparse tables, which is again very nice. It's not that straightforward like prefix sums. So I will start with sparse tables. And now you might think that as a beginner, you might think that you can extend the same thing to answer minimum queries on an array. Like rather than answering just sum of a subarray, you might think that you can also do minimum on a subarray, but it's not true because that part where you say that sum of the arrays pr minus pl minus 1, this doesn't necessarily hold for the minimum, right? I mean, you can't really subtract minimum or something like that. So minimum, even on a static array, handling minimums is not that simple. That is why we have sparse tables for static arrays, where the array does not change between the query. The array is given at the starting, it is fixed, and then you only have queries to answer stuff. You don't have to change elements in the array. That is what static array queries means. And then you have dynamic, that you will be learning in a future, like I think the next lecture, segment trees. You will be learning how to handle dynamic stuff, like the value of the array will change between queries. Somebody else will take a lecture on that. So now we'll look at a problem. I'll just write the problem here. You are given an array again, a1, a2, a3 up to an, and the n, again n can be up to 10 to the power 5. You have q queries 10 to the power 5, and each queries of the form l to l comma r. Find the minimum of all the elements. So this is the motivation problem. So, and again, you can't actually go through the elements because that will go up to n into q, o of n into q. That will be 10 to the power 10 operations, which will of course TLE. So everyone understand the motivation problem? You want to find minimum of subarrays, right? So to find minimum of subarrays, now what we could do is, like I will give two inefficient approaches. You can also use this for the sum also. Like the first thing is, don't pre-compute anything. Just answer queries on the go. That is what I said. It will reach n into q. Then you would have 10 to the power 10 operation, which is again too expensive. Or let's say you pre-compute everything. You pre-compute every single possible L to R, and you can answer queries in O of 1. But then again, pre-computing that is too costly. That will become the bottleneck of the program. So now we need a compromise between how much we pre-compute and how fast we answer queries. So that's where sparse table, you can see that clearly in sparse table. It is a compromise between how much you pre-compute. Actually, even in sparse table, you actually, bottleneck is like what limits the program. Like for example, you have something like O of n square plus m, any time complexity, some time complexity. Let's say n is nm are less than 10 to the power 5. You would not write it as O of n square plus m. You would write O of n square, right? Because m is nothing. 10 to the power 5 is nothing compared to 10 to the power 10. So the bottleneck of this program is the part that has n square. So that's what bottleneck is. The part that's actually making your code slow. So pre-computing, as I said, if you pre-compute everything, that is the bottleneck. That will make your program slow. And you can answer queries no often, but there is no use. The pre-computing will take so much time. That is bottleneck. So now we need a compromise on how much we pre-compute and how quickly we can answer queries. So the question remains, like, how much do we pre-compute? And sparse table is that idea. Like sparse table, it might take you some time to like get a hang of it. So I will just go through it. I'll state it formally. Do try to think about it for some time. A2, A3. So as I said, the naive approach would be to calculate literally every single subarray that would exist O of n square. Actually, that would just exist n squares. Something quadratic n square subarrays, which is too much. But sparse table doesn't exactly have an n pre-computation like prefix sum. It is slightly more than that, but it is still better. Sparse table says compute the sum of every subarray that has a length of power 2, like a power of 2. So it says compute the sum of having length 1, 2, 4, 8, and whatever up till n, whatever log base 2 of like the nearest power to 2 of n is the lower power. So you would compute the power of A1. So you would have the answer ready for 1 comma 1, 2 comma 2, 3 comma 3, up to n, because of course, that is nothing, that is trivial. Basically just the element itself, because subarray of length 1. And we would also have the answer for subarray of length 2, 1 comma 2, 2 comma 3, 3 comma 4, and so on, n minus 1 to n. And subarray of length 4, actually this 1 comma 4 is the indices, okay, like a1, a2, a3, a4. 1 comma 4 means that 2 comma 5, 3 comma 6, and so on till whatever n is the rightmost endpoint. And we will do this for all the powers of 2. Does this make sense? If you didn't understand, I can explain it again. So we will not compute 1 comma 3, simply because it is not a power of 3, right? 1 comma 3 has a length 3, and 3 is not a power of 2. Sorry, power of 2. 3 is not a power of 2. And we will not compute 1 comma 5, because again 5 is not a power of 2. We will compute 1, 2, 4, 8, 16, 32, and so on. And can anybody tell me, like amortized, like, sorry, I mean worst case, how many arrays would you have computed? Like how many such arrays can exist, like maximum in terms of n? How many such sums will you compute like this? Can you give me an upper bound on that? It's not hard. Yes, it is n log n. Someone said n log n. It's correct. Because think of it, actually n log n is an upper bound. I think it's actually hard to achieve n log n, but it's a good upper bound. So I will explain why n log n. Because there are n elements, and starting from each element you can have up to log n, right? Because you are computing like literally every power of 2, and you can have up to log n. So for each element there are at most log n, like subarray that you will calculate. So because there are log n powers of 2 less than n, right? So does that make sense why the upper bound is n log n? And it turns out, fortunately, that this much and only n log n precomputation are enough to answer any minimum query in O of 1. So I'll show you how. Now that we have computed all these things, now I will show you that you can give me any subarray of this array, and I will just using any, like using any two of these things, like just two. I can combine any two of them, and I will get the minimum of that subarray. Okay, why it? Someone wants me to explain why it's n log n. Uh, you understand that there can be at most log base 2 n powers of 2 less than n, right? That makes sense, right? Yes. So like n log n is a worst case. Like it is actually, the answer is lesser than n log n, but even the worst case is fine for us. So let us say we're right now at 1, and let's see what all powers of 2 can be computed. 1 comma 1, that is length of 1, 1 comma 2, 1 comma 4, 1 comma 8, and 1 comma 16, up to the nearest power of 1 comma, let's say n is a perfect power of 2 to keep the discussion simple. So the person who has a doubt, can you tell me like how many such things can you have, like how many such terms can you have in this, where the left hand term is only 1, 1, 2, 4, 8, 16, up to n? How many terms can this be? Yes. So and the left hand point can be up 1 to n, right? So n into log n is n log n. Does that make sense? Okay. And you can notice that after some element it will not actually reach log n. It's actually an upper bound. It will never actually achieve that value, I think. And now using this data, so using just all these pre-computations, we can answer any subarray using just combining two of these pre-calculated values. We can now find the minimum for any subarray. So I will explain how. Let us say we have a subarray that we want to calculate the minimum of this, and the whole array is something like this. The shaded part is what the minimum that we have to calculate for. So from the starting point, we have every power of 2 up till n, right? Like the length is like every power of two's length we have come starting from this element here, something like this, something like this, something like this, and this so on. So now what we will do is I will divide this into two cases to make so that you people understand. Let us say that this whole length is a perfect power of 2. Then this would, like, this entire block would be present somewhere over here, right? Because we have by definition we have computed everything that is the perfect power of 2, that has a length that is the power of 2. So if, let's say, if this was a perfect power of 2, then this would be included here. That makes sense. So we can just directly get the answer from that pre-computed value and just give it. Does it make sense? Like, we just, if we already have this pre-computed, we would just give that. Like, we would just output that value because we're already having it here. Let us now, we have to go to the case. I mean, the input can be anything. It doesn't have to be a perfect power of 2. So now we will go to the case where it doesn't have to be a perfect power of 2. Let us say it is something like, let's say 11, which is not a perfect power of 2. The length is 11. The length of the subarray that we have to calculate for is 11. Again, I'm not taking the indices like I, j because it is irrelevant here. We have computed for everything. I'll just symbolically show how we do it. So now we will take the largest power of 2 less than the length of this array. So can anyone tell me what is the largest power of 2 less than 11? Yes, it is 8. So now we have computed from this lth element, we will take a length of 8 that would look something like that. We already have this value, right? Does that make sense? We have computed this value. Can you see that the right part, some part is not covered because 8 is less than 11. So there would be 3 elements that are not covered to the right. Yes. And now what we can do is we can also use a length of 8 like this. Like, it would be some element from here. I don't know. Maybe it is the third element after L or second something. So I will now combine these two, and you can see that every element is covered. The minimum of that and the minimum of that. The minimum of those two would be my answer. Does that make sense? Like, I have two ranges which are covering the entire subarray that I need the answer for. And since it's minimum, it doesn't matter if I'm covering something more than once. The minimum won't change. If it was some, then I would be overcounting. But then I only care about the minimum. I know the minimum in this, like minimum for all these ranges. So the entire subarray that is in consideration is covered by these two ranges. If you didn't understand, I can explain. Okay. So that is how it is. Now you can see that the time complexity is O of 1. If it was the perfect power of 2, you just need to check one value and you can output it. If it is not a perfect power of 2, you need two ranges, and that is O of 2, basically O of 1. Now the question remains is how to calculate this O of n log n stuff efficiently, because this should not become a bottleneck, right? And if you didn't think about it, actually calculating this was not very trivial. Like, because we have to calculate this efficiently. We can't actually, go through everything and do the sum. Then again, it would become, I think, n square log n. It is worse than the naive problem, like the naive solution. So the question remains, how do we pre-compute this efficiently? Can anybody give me an idea? I think you would have watched the binary search lecture, and there would have been something like binary lifting. Did you people learn binary lifting in the binary search lecture? Because the idea is similar. If you can correlate it with that. Okay, you did not learn binary lifting. Okay. If you had known that, then it would have been easier, but I will explain it. And this idea is very important. This pre-computing method is very important because the same idea is used in binary lifting, and it's a very important topic in trees. It's reused a lot. This idea is reused a lot in computative programming, so it is a very important idea. So now, of course, the base case, right? These are length of 1. This is very easy to compute because it is literally length of 1, just the element. Like, you can easily compute, right? Minimum of 1 comma 1 is nothing but A1. Minimum of 2 comma 2 is nothing but A2. 3 comma 3 is A3. So that is very easy. So now what I will do is I will store a 2D array. Let us say RMQ, range minimum query. I will call it RMQ. The array is called RMQ. Something like this, n log n. This is the size of the array, by the way. it is a n into log n array. Like you have a DP array n into n, right? There n into n, like a 2D array. This is n into log base 2n. Now I will define formally what RMQ I comma j stores. RMQ I comma j stores the minimum. So basically, like here I had defined. Okay, someone is asking why can't you use segment tree? Yeah, you can use segment tree, but then there are instances where sparse table is required because see this is a very basic motivation problem, right? And segment tree is overkill. The log factor from a segment tree is much slower. It is actually 4 into n and stuff. The memory also is high in segment tree. And normally sparse table is not used alone as a problem. It is used in a DP optimization. And sparse table allows you to do O of 1. And segment tree is O of log n. So in those learning sparse table is very useful. Even Fenwick trees, you can ask the same question: why do you have to learn Fenwick trees when you already have segment trees? The answer is segment tree is very slow. You might get TLE when you're trying to optimize your DP. Does that make sense? Because in DP you do not just have log n, you have something like n square into log n, or maybe n log n. And the log from a segment tree is slower than the log from a Fenwick tree or a sparse table. And sparse table you can do in O of 1, which is much better when you're doing DP transitions and stuff. Does that make sense to answer your question? Okay. There are many instances where segment tree TLEs, but then a sparse like a Fenwick tree will pass or a sparse table optimization will pass. Okay. So RMQIJ is nothing but the minimum of AI plus one, AI plus. So basically, I'm saying RMQIJ is nothing but the subarray starting at I and length of 2 to the power j. Does this make sense? Basically, what I have defined here, I'm writing it in a different way. This part that I had defined, I'm writing it in a different way here formally in terms of RMQ because I need to store them in a DP array, right? All these are like pairs 1 comma 1. I need to store their minimum. This would be the minimum of AI plus 1, AI plus 2 up to the length 2 to the power j length. If this makes sense, do let me know or I will explain it once again. Does this make sense? Okay. So we will do something like an inductive step here. Let us say we have calculated for some j minus 1, RMQ I j minus 1. Everything of j minus 1 is calculated. The way we are doing it, we will calculate everything for length of 1, all subarray of length of 1. Then we will calculate for all subarrays of length of 2, then all subarrays of length of 4. So when you're calculating for subarrays of length of 2, everything of subarray of length of 1 is already calculated beforehand. So now we will see how to use the data of subarray of length of 1 and use that to get subarray of length of 2 data. So let us say we are calculating for subarray of length of 4. 1, 2, 3, 4. Let's say I is some 3 and length is 4, so j will be 2 because 4 is nothing but 2 square. So let us say we want to calculate the minimum in this efficiently. We can't actually go through these 4 elements and take the minimum because then I told you, right, it will reach n square log n, which is worse than the like uh, just going through the elements O of NQ approach. But we are trying to do something better. And we have calculated for everything of length 2. So that means we have the answer of 3 comma 4 and 5 comma 6 already calculated because I told you, right, we will only process length of 4 when we have already done length of 1 and 2. So right now we are trying to calculate this length of 4. So that means length of 2 is already calculated. So this length of 4 answer is nothing but the minimum of 3 comma 4 and the minimum of 5 comma 6. Does that make sense? Uh, the length of 4 is nothing. I can combine two length of 2s to combine them and make a length of 4 because because of the simple reason 2 comma 2 to the power j is nothing but 2 into 2 to the power j minus 1. So I can add a smaller power of 2 to get the next power of 2. Similarly, to calculate a length 8 like this, I would combine the answer of the first 4 elements and the last 4 elements. Does this make sense? How I am calculating this efficiently in O of 1. I'm just using the previously calculated values and I'm combining those two to get the length of 8. I'm combining two 4s to get 8, two 8s to get 16. Does this make sense? It is a kind of a DP, you can say. It's just a little different, a different DP. So now I will write it formally. RMQ I to j is the minimum of RMQ I to j minus 1 and RMQ I plus 2 to the power j minus 1. Does this make sense? This transition that I've written here, the recurrence, basically RMQ I comma j. The minimum of the element from starting from I and length 2 to the power j, I'm writing it in terms of subarrays of length 2 to the power j minus 1. Does this make sense? It is the same idea is used in binary lifting also when you're calculating a kth ancestor. That is in a future lecture you will learn about it. So if you have any doubts in this, like if you didn't understand how I'm calculating this, it might be difficult for people learning it for the first time. So if you have any doubt, you can ask. Okay, I'm assuming everyone understood. And to make things even more clearer to you, I'm going to show you the implementation. I'll just share my screen. Give me a minute. Okay, I'm sorry. Yes, somebody said it should be 2 to the power j minus 1. Yes. In this transition, it is 2 to the power j. I said right, it is 4 and 4 to combine 8. So if j is 3, then it should be j minus 1. Oh, that's what you meant, right? The transition 2 to the power j minus 1. Okay, I'll share my screen quickly. Can you see the implementation? Yes. This is the CSEO standard problem, by the way, static range minimum queries. Do let me know if you can see the screen. I'm not sure if you can see my screen. Okay. So the code is also quite short for sparse, like sparse table compared to segmentary. You can see it's actually, this is all the code there. The implementation is very concise. This is just the base case. I'm taking input. Actually, just look at the problem. You're given n integers, task to process q queries of the form. What is the minimum value in range a to p? So I'm taking in the integers, and I've chosen 18 explicitly here as login because I think it won't exceed that. As I said, that RMQ had 18, right? And I'm setting mi0. 0 means 2 to the power 0. That is 1, length of 1. And that I told you, just the element itself. That is what I'm doing here. Then I'm going in increasing order of k, increasing power of 2. I'm calculating 2 to the power 0 first, 2 to the power 1, 2 to the power 2, and so on. And I'm calculating the values based on the powers of k minus 1, as you can see, the same recurrence. By the way, this bit shift is nothing but 2 to the power k minus 1. This 1 less than k minus 1 is nothing but 2 to the power k minus 1. So now the pre-computation is done. This is all the code of pre-computation. This is a bottleneck basically. It's n log n because 18 is basically log n, and this can have up to n iterations. So n log n, and you can see how I'm answering queries. Taking in LR, then I'm seeing the length. I'm taking the largest power of 2 less than or equal to it, and I'm answering it. I'm basically combining those two to get the minimum of those two, and that will be the answer. That's all sparse table is about. Do you have any doubts in the implementation? You can ask. Okay, so I'm assuming that you understood the implementation. Can you tell when to use mainly? I have sent a problem. Have you looked at it in the group? Yeah, the problem is hard. Like mostly they are used in DPU optimization. Like if you use sectree, you will probably not pass that problem. You will get a TLE because it will have a log and a slow log at that too. So you have seen DP problems, right? Like where you have states, you want to calculate the minimum of something in that state. Have you seen such DP problems? Yeah. One thing you can do for the minimum is you can actually go through that entire thing and you can add a extra n to your complexity and make it slower, or you can use a segment tree to get the minimum, or you can use a sparse table, which is much quicker, provided that the elements don't change. And remember, sparse table is only when the elements don't change. It is called static range minimum query. The array is static; it doesn't change through updates. That is when you use a sparse table. When it has to change, I think that you don't have an option other than segment trees. Yeah, family tree is only for some. So you don't have a choice if it changes. You have to use segment tree. But when it doesn't change, you can use sparse table. This problem is slightly hard. It's like a 2100, I would say. But like the hard problem is not the sparse table, but it is the problem itself, the ad hoc part of it. The sparse table part is quite trivial. So do try this problem like when you get better or something. Or you can try sparse table motivation problem. You can try to implement sparse table and submit the CSCS problem to make sure you understood the implementation. This is not a DP, by the way. I didn't say this is a DP. I was just mentioning general DP. It's kind of an ad hoc, I would say. It's kind of something on its own. I mean, you can call anything a DP like that, but it's not a classic or a standard DP type of problem. But it's a nice problem nevertheless. It's something you should try. Like if you're having no idea, then you can like try it after a month or something. But the sparse table, you need sparse table in this problem to solve it. That's why I shared this problem. Without sparse table, you would only get like 40 points. You would get TLE in all the subtasks. But with sparse table, you can easily get AC. Like the time limit is very tight. Even if you use like C plus, my solution passed in C plus plus 20, but not in C plus plus 17. So I'm sure if I had used a segment tree, I would have failed. Like it would have gotten a TLE. So this was I want to give an example of an example where you have to use sparse table. And this is just a general advice. Do not always try to use segment tree when you don't require it, because I think there was an instance where INOI 2023, probably problem 3, where it had Mohs algorithm, O of n root n log n, which is like a very high time complexity. And people had the exact same solution with segment tree and with Fenwick trees. The people with segment tree did not pass, like they couldn't get it to pass, even though the theoretically the time complexity was same, but practically like it was giving TLE for them, so they couldn't pass it. So I would say if it is static and you don't need to change it, then I would suggest you to use sparse table and Fenwick tree if it is some. But don't get confused. I didn't teach Fenwick tree this class. Fenwick tree is something different. You will learn it later. But sparse table, if it's not changing, if it is static, then do use sparse table. Yes. So that's it. If you have any questions related to any part or you want to like see the notes, I can show. And I think theory wise, we are done for the session. Okay, I'll end the lecture. Uh, you can try problems from Utako Guide or any. I mean, you will find a lot of secondary problems. But sparse table, as I said, you will not have a problem that has only sparse table. It will have some other thing. Sparse table will be a very small part of it. So I can't really give you problems with that, like that is intended with sparse table. It will be a small part of it. Like as I even I said the problem now, the hard part of the problem is not the sparse table. It is actually solving the problem, reducing it and simplifying it. That is the hard part. So okay, we're done. Okay, I'll end the session now. Yes, thank you.